Good morning, good afternoon, everybody. Welcome to the revitalization of our Storms of the Month here at the Warning Decision Training Division. I'm Chris Finagle. Our first presentation will be by Jim LaDue from the Warning Decision Training Division and also Dan Bikos from CIRA. It's going to be on characterizing the 29 November 2019 Phoenix tornadoes.
Thank you very much, Chris. Dan Bikos with CIRA is with me, and I also want to give a shout out to Paul Iniguez, who I've been in contact a lot with regarding this case, which was really interesting. The reason why I did this one here is because I actually happened to be vacationing out in Arizona, visiting family in Phoenix. When 4 in the morning, my phone suddenly starts going crazy with a tornado warning. And so that's not something that Phoenix experiences very often. And so I thought this would be really worth taking a look at. Especially since it was really, if you go back to 2010, the last time that something like this had happened. It was a busy morning, as you can see here. Just about every kind of watch warning was available here or issued, maybe except for perhaps fire warnings, and that's about it. But certainly this is a couple hours after the main event that I'm going to talk about, and there are a lot of aspects to talk about during this event, and I'm really just going to zoom in on one specific question here, and that is taking a look at the origin of these events. So let's take a look at the storm reports. This is the general storm reports after, let's say the 29th was over with. The red polygons represent flood or flood reports. Then we have numerous wind and 4 tornadoes actually in the Phoenix metro area. I'm specifically going to look at the ones just north of Phoenix here and just kind of zoom in on that a little bit more detail. So here we are. We have 2 tracks that are of special interest. One of them here starting at 10:49 UTC. So this is in the dark 30 hours here in the morning with a 100-yard wide tornado that tracked for 10 miles. And then another one here just a little bit later, almost simultaneously, going through the Phoenix Mountain Reserve and then going up to Paradise Village. So this is a crowded area. And luckily, these tornadoes weren't that strong. So this is not a disaster per se, but a very interesting meteorological case. But you can see some of the kinds of damage that were reported. There were even saguaro cacti that got knocked down onto cars and shingles, roof shingles, and things like that, carports. That was the level of damage there. Dan Bikos is with me, and so I'm going to go ahead and have him talk about the larger scale pattern here, and we're going to look at the GO 17 air mass. And Dan, what do you see in this one here?
Thanks, Jim. Yeah, this is the GO's air mass RGB product. It makes use of 2 water vapor bands along with the ozone and IR bands. The dark red to orange colors identify ozone-rich descending stratospheric air associated with the PV anomaly. And this is associated with a region of relatively low tropopause height. And you can see that's approaching our area of interest in Arizona. The consequences of this are that convection will be relatively low-topped. In this cold season environment of marginal cape and low-top storms, it would be wise to adjust the IR color table towards warmer brightness temperatures, which we'll demonstrate later. Turn it back to you, Jim.
Yeah, thank you very much, Dan. And let's go ahead and take a look at those cold temps aloft and just enough moisture down below. And we managed to squeak out about 100 to 400 joules per kilogram of CAPE, especially down here closer to the Sea of Cortez where the flow is coming right off the water there. But you can see on the shear side of things, no problem, no limitations with shear. So let's take a look at this this 17-hour. I don't know why I picked 17-hour, but I picked the the NAN nest from the previous day and looked at the forecast soundings for the Phoenix area. And by the way, this is pretty close to what actually happened. But you can see that the CAPE is pretty thin. Buoyancy is thin, but on the other hand, you also don't see any inhibition at all. Lapse rates at 4 in the morning were forecast to be pretty much fairly steep right off the ground, and with the boundary layer up to 150 millibars deep of near saturation. So that's the thing that is interesting, and I'm going to refer to later on as we continue this. But overall, the CAPE is so thin on this date, it's more akin to a narrow cold frontal rain band kind of setup than, let's say, a higher CAPE QLCS kind of setup. But let's take a look. Take a look at the photograph. It's really got strong shear. 51 knots of 0 to 1 kilometer shear in the lowest 0 to 1 kilometer, and 60 knots in the 0 to 3, and up to 75 to 76 knots through the lowest 6 kilometers. So the only thing I could say that would be a weakness of this is that we don't actually have pure streamwise vorticity. In other words, the shear completely perpendicular to the low-level inflow coming in to the storm. But if you shave 51 knots and divide it by 2, you still get 30, close to 30 knots of shear, 25 to 30, which is very significant. And given the relatively large storm-related felicity, we do have some sigtor values. They're only limited by the lack of buoyancy here. So let's take a look at the forcing mechanisms. Okay, so the cape is thin. If we had individual cells, they'd be ripped apart by the shear. But in this case here, we have a strong forcing mechanism. It's a cold front, Pacific front coming out of the west. And you can see the dew points 50 to 54 degrees coming out of the Sea of Cortez. Temperatures at 4 in the morning in Phoenix were 60 degrees, so that's pretty warm. And so let's go ahead and zoom in and show you exactly what happened. And we're going to look at the TPHX radar. Yeah, this is the Phoenix TDWR. And one thing of interest here is I have 2, 3 vortices that started up immediately. These are fairly weak to begin with, but over time we have 3 more vortices that eventually dominated the picture and then took off to the northeast, vortices A, B, and C. So I'm going to look at why did these 3 suddenly form so quickly, and then what was going on as we started seeing the rest of these things. So the key thing here is I wanted to go ahead and point out and reiterate some of the vortex formation mechanisms with this line of storms that came through. And the first one is the origin of, let's say, the tilting of crosswise vorticity by the downdraft. So this is when you have a situation where maybe you have a big downdraft that suddenly dropped down on top of a field of horizontal crosswise vorticity on the interface and behind the cold pool boundary. So this would yield counter-rotating vortices with the anticyclonic vortex to the left of the cyclonic if you're pointing down in the direction of motion, if you're viewing this in the direction of motion from behind the storm. The other possibility is that we have tilting of crosswise vorticity, and this is actually Atkins and Lawrence. The other one was Trapp and Wiseman's paper. So Atkins and Lawrence says, well, maybe it's actually the tilting of crosswise vorticity by the updraft along the cold pool interface. So here are the vortex lines, and we had this surge coming out. It's kind of like a bow echo formation process, and we have this surge of updraft as a result, and the tilting of the vortex lines like this. Now we have the cyclonic on the left and the cyclonic on the right, if you're pointing downstream. And this would have to form, of course, with a cold pool, some kind of baroclonic force. Tilting mechanism, or let's say mesovortex formation mechanism 3, is the tilting of streamwise vorticity by some local updraft, but the streamwise vorticity is on the cold pool boundary and then behind the cold pool, actually. And so streamwise vorticity is coming in, and then it encounters an enhanced updraft and gets tilted up, thereby continuing this this vortex or producing one. So this one also requires a cold pool of some sort. Number 4 is the horizontal shearing instability. So now we have multiple vortices forming concurrently, roughly evenly spaced about 7.5 times the width of the boundary. And this often happens when vorticity ramps up in an unstable atmosphere. You would often see along this boundary large horizontal wind shifts of greater than 90 degrees, and there might be an inflection in the wind vector as you cross the boundary. So here's Craig Forbes talking about horizontal shearing instability at a recent talk. And there's a paper, Clark and Parker, that looked at numerous events in Great Britain. So needless to say, given the similarities in the climate between Great Britain and Arizona, this is the paper I'm going to go ahead and take a look at in a little more detail. So we're going to look at the vortex spacing to start off with. And this is what it looks like. So if I took the spacing between each vortex in this, and I'm not actually looking at A1 through 2 in this case, but they were there earlier on. And when I took a look at them, And I looked at the width of the boundary. So the width of the boundary I wound up looking at the TWR and looking at where the wind was homogeneous in front of the boundary. And then as soon as it started changing and shifting across the boundary, I would mark that as the width up to the post boundary where the wind settled down into the post boundary environment. So that was the width that I picked, and it was pretty darn narrow. This boundary was down to roughly 300 to 500 meters. I'm going to pick 300 meters here. And the spacing between the first three mesovortices are plotted here, and you can see they line up pretty well with the 7.5 times the boundary width rule. Later on, though, with the subsequent boundaries and the spacing between them, between B and A, B and C, and then eventually A and D, you can see the width, or let's say the boundary spacing, increased, and so it wasn't any longer representative of that 7.5 times rule. So that's an interesting thing, and it looks like, hey, that might be a candidate for horizontal shearing instability, that's for sure. But let's take a look at others. And one of them is taking a look at the surface plot. And in this case here, I'm looking at the surface plot of an APRS station right in the vicinity of where these mesovortices started. And I'm plotting the wind direction. And what I'm doing here is I took the mediogram and converted it to a time space relative to the front position. So here's the front crossing that station. So this is the prefrontal wind direction and temperature. And you can see the temperature drop and the wind shift. And you can see the wind shift is roughly 100 degrees. So that's pretty dramatic and large amount of wind shift there in a short order. So that also says, yeah, okay, there's some potential vorticity. But here's another thing too. I want to take this boundary, I want to compare it to that forecast photograph and take a look at how the flow is oriented relative to the reference frame of the front itself. So here's my front right here moving to the east, 28 knots. And the interesting thing is that if I took a look at the convective layer steering flow, which is represented by this brown square, you can see it resides right on the front. So that means the storm or the boundary relative convective layer steering flow is nearly zero. It's literally riding the front like a surfer. And so that promotes updraft longevity on the front and increases it. Similarly, we know in the 3 ingredients rules for QLCSs, you know, those that are favorable for producing these mesovortices, is that we'd like to have substantial boundary normal component of the 0 to 3 kilometer shear. And so I visualize that component right down here. It's roughly about 30 knots, which is fairly favorable. The length of this vector being roughly 30 knots, if I move that vector up to here with the tail of the vector at the origin of the photograph. So all these things, all this kinematics show that we have a front that seems to be very conducive to allowing updrafts and deep updrafts to reside on that boundary for a long time and maximize the potential vorticity for whatever vorticity is available for stretching. And so that's the next thing I was saying to look at, how much vorticity is on this boundary. And I'm going to do it in a way that makes some assumptions. And one of them is that I'm going to assume that the vorticity along this boundary is fairly similar. And so that I could take this mediogram and actually take the time to space and calculate kinematic variables out of it, vorticity and convergence. And if I multiply the vorticity and convergence with this time to space method, I get stretching potential. And so with this station here, I have a lot of noise. And it's because there's a lot of gustiness and so forth with the pre-cold front air mass with a strong low-level jet and instability. I get a lot of gusts. There's horizontal rolls in there and so forth. But the other thing too is that the station has actually not got the best exposure. And so we have a complicated picture here. At least though on the front, I do have positive stretching potential. So maybe I want to take a look at another station here. And this one is the Phoenix METAR site at the airport. And here, much better exposure, shows much smoother flow. A little bit of bumpiness ahead of time, but take a look at the stretching potential right on front. It goes right off the top of the chart. So that gives me a lot more confidence that yeah, we got vorticity here, and we got strong stretching potential, and the front riding the boundary. Let's say the deep updraft steering flow is riding the boundary, plenty of time for developing these vortices. We know we have vorticity and we got stretching along that front, courtesy of some of the observations where the front passed. And so let's go ahead and compare the peak vorticity and stability that we found for that Phoenix area, that Phoenix METAR site. And I'm going to use a form of stability called the Brunton-Weissler frequency. And that is basically that equation down there where you see it's a function of the difference between the theta E down at the surface and then the saturated theta E aloft over a space or depth of 1 kilometer. So I'll take a look at that, and I did calculate it. In fact, you can actually use these variables from the volume browser in Ellipse to calculate a frequency of negative 0.2. In other words, it's unstable. And the Brunton-Weissler frequency is unstable. Think of the Brunton-Weissler frequency as kind of like an air parcel. If the air is stable outside the parcel, and you launch the air parcel like a balloon, the balloon just oscillates up and down and then comes to rest somewhere. But when it's unstable, then the balloon just takes off, much like convection. So that's what we're seeing here. It's below zero, and the Phoenix site at that time had a negative Brunton-Weissler frequency. At the same time, it also, when the front pass, had a positive vorticity, a maximum vorticity. And so we compare the two here with previous tornadic versus non-tornadic cold frontal rain bands in Great Britain, as I talked about before, from Clark and Parker in 2014. And you see the Phoenix ob lies within the realm of the tornadic realm. In other words, in the distribution of the tornadic narrow cold frontal rain bands in Great Britain. So it kind of makes sense along with this one. So I think that really kind of says it all right there. We did have something that does make sense with previous studies, even if it is from Great Britain. And there's positive streamwise vorticity back here, and that's being fed into the front itself. So with the baroclinic forcing and this positive shear behind the front, it's still got that environment that says, yeah, mesovortices can still occur. So if I put it all together, I get this, and I have the 4 terms up here, the 4 possible origins of mesovortex forcing. We can immediately discount anything with tilting of crosswise vorticity. We don't have any couplets. So that leaves the tilting of streamwise vorticity and the horizontal shearing instability. And both of them, what I've gone through says both are probably responsible for this. But given the spacing of the vortices to begin with compared to the boundary width, I think the initial vortices were mostly streamwise or HSI, whereas the increased spacing is going into the tilting and streamwise vorticity, maintaining those. So let's take a look at why, and is there anything that we could see that would give us lead time to watching or at least anticipating formation of mesovortices. And so in this case here, I'm going to go to Dan, and he's going to talk a little bit about the next couple displays here.
Thanks, Jim. In order to address what clues to vortex stretching exist, we'll take a data fusion approach and consider the GOES IR imagery along with the GLM flash extent density and MRMS products. Note that the brightness temperatures in the IR imagery are mostly in the same green to yellow range, which is around -50 to -60 Celsius. This makes for poor contrast to view the storm tops of interest in the default color table. So next we'll change the color table towards warmer brightness temperatures, and we'll also adjust the data range for the GLM flash extent density to highlight lightning activity for this time period. So now we've changed the IR color table to the GOES snow squall color table, which is useful during cold season or when you're expecting low-topped convection, since you have increased contrast. And I've also changed the GLM flash extent density range from 1 to 256 to 1 to 15, and that's just based on a quick look at convection with your ellipse cursor readout. So don't hesitate to change color tables or data ranges to meet expectations for a given event. In the IR imagery, we can now see cloud top cooling trends pretty clearly in the expansion of these colder cloud tops. In the GLM, in the upper right, we see lightning onset, and also the indications that the updraft at -10 has exceeded 5 meters per second from that lightning. In the MRMS reflectivity in the lower left at -10, we do see a weak increase in the reflectivity, and in the bottom right in the MRMS as in useful CIRA, we do see an increase there as well. Next, I'll turn it back to Jim, and he'll look at time trends of these fields.
All right, thanks, Dan. And so here's the first lead up here is the GOES 17 cloud top temperature min, and I'm using the tracking meteogram here, by the way, so this is something you can actually do as well, although it does take a little time to set up, so it's not exactly a warning tool, but it's a great analysis tool. So you can see that drop in the IR cloud top temperature min here, and you can see then that occurs first, and then the cloud, the flash extent density and the GLM starts piping up roughly about 10-20 minutes later. The reflectivity at -10 is kind of bouncy. It's all over the place. And so it's a little bit less confidence here as to what's going on. And it's probably, because the reflectivities are weak anyway, this is a rather tenuous situation. But here's the azimuthal shear. You can see there's a little bump up and then a dramatic increase here. And that follows the increase in the GLM flash extent density. So all indications are updraft forcing first, and then the MRMS is detecting that shear along the boundary next. So if we put it in a timeline mode, here it is. We start off with the day one outlook. Actually, the CAMS models did pretty well. The NAM-NEST was forecasting helicity tracks, and so was the HER. SPC put out the marginal risk. And then later on, 1 hour lead time, we have the cloud top temperature cooling. First indications of updraft growth, at least at this point here. So satellite gets it, and then the GLM starts cropping up, roughly about 30 minutes, 40 to 30 minutes lead time. And then we see the collapse of the funnel width, the sharp wind shift. Both radars, that is, the TDWR and the 88D, show the same thing. And then the peak as shear starts really bumping up here. So then the roll up into the vortices followed after that. So overall, I think we've seen that we're looking at horizontal shearing instability here, maintenance of streamwise vorticity, and then see what kinds of precursor signatures there are given the data that we have in this case here. We're fortunate we have really awesome meso network over Phoenix, and we have TDWR and radar. So you can imagine, in some places there are certain things you can't do. So with that, I'm going to go ahead and stop there and wait for any questions.
Alrighty, well then with that, I will go ahead and conclude our first revamp of the Storm of the Month. Thank you, Jim and Dan, for coming in and doing this shorter notice Storm of the Month webinar. We're really excited to be working with everybody on this, and we appreciate the really high attendance today. So thank you again, and be on the lookout for the next announcement. Thank you, everyone.